Uh, Good morning, everyone. It's me, Dr. Irfan Ahmed, and today's presentation actually will cover about what's one of the most hot topic in the statistics. It's about the parametric and non-parametric statistics. In this presentation, we just cover about when to choosing the parametric statistics and when to choosing the non-parametric statistics. Okay, it's not mainly on the parametric statistics and non-parametric. It's just about the main information about when we are choosing the parametric and when we should choose the non-parametric statistics. Okay, it is the main outlining of this presentation, like when we choose and when to choose para and when to non-para, then and what is the normal distribution and skew distribution, and then we do a practical demonstration by SPSS, like what we do the normal, how can we find out our data is normally distributed or our data is skewed. Okay, then the advantages of parametric statistics and disadvantages of non-parametric statistics, and how to deal with non-normal data or skew data, and dealing with a data transformation. For example, if our data is like skew data, so how can we transform it to the normally distributed data so that it allow it so that it cover the assumption of parametric statistics. So we do the practical demonstration using SPSS of these steps and the transformation steps. Okay, so I now come toward the next slide. So when to choose para and non-para? Actually, there is three main assumptions when we want to choose whether we should choose, when we look to the data and we decide whether we should use the parametric or we should use the non-parametric statistics. So these three are main assumptions. Number one, the data should be, when we see the data, actually when we look to the data should be interval and ratio scale. Okay, if the data is in the categorical data, then we cannot use no parametric statistics. Okay, so the first main assumption is interval and ratio scale. The second main assumption is the data should be normally distributed. Okay, so how can we know that our data is normally distributed or not normally distributed? So we use the different different tests, but luckily it's now due to SPSS, it's very easy. We just in a few steps we know that our data is normally or not normally distributed. We will cover this in the coming slide using a practical demonstration by SPSS. The third thing is homogeneity of variance. Okay, if the data is have the homogeneity of variance is assumed in our data, so we can use the parametric statistics. If anyone and these three is missing, okay, like these three is a compulsory thing, either of one is missing, we cannot use parametric statistics. Okay, these three are the main things when you are deciding for the data parametric or non-parametric statistics. Okay, now coming toward the next slide, which is okay, normal distributed. The first thing is like when we see the data, it can be easily uh, we can easily get that whether the data is like interval scale, ratio scale, or like categorical data. Okay, so it can be easily you can easily reach the conclusion about the data when you look to the data. Okay, so no need to worry about that, so you can get it easily. But the main thing to worry about is actually normal distribution. Okay, because you cannot reach the conclusion when you just look to the data. You have to apply some statistical test. So so most statisticians prefer that you should follow these three things. Any of one can be okay, but most statisticians prefer that you should follow these three or these three whenever you are deciding whether your data is normally distributed or not normally distributed. The first one is descriptive data. Okay, you have to describe using the special type of SPSS statistics tools, using the special type of test and the SPSS, and you describe the data in order of mean, median, mode, and 5% mean. Okay, so when you describe it and you just see the descriptive table, you can get the idea of your data, whether it is normally distributed or not normally distributed. The second one is the graphical analysis. The graphical analysis is like we can assess by making a graph like a histogram, Q plot, stem and leaf, and box plot. which we will cover in a practical demonstration of this presentation. And the third one is most important is the statistical test. We have the chromograph and the Shapiro will test. And the chromograph, we have two chromographs in all, and the chromographs in all goodness for fit test. If we have the large sample size, for example, if our data is like uh, if our data is more than, for example, is 30, so we can use the Shapiro well test. But if our data is less than 30, so we mostly prefer Lomogla. Like if less than 30, so these two tests is okay. But if it is more than 30, then we use goodness of fit test. Now coming toward the practical demonstrations, we want to share the mean of the SPSS. This is like the data set here. Now this is the SPSS file, as you all know that. So if we want to know that whether our data is normally distributed or not normal, we have to, like, this is our data, this is the ID, this is the age of the participant, this is the gender, BMI, this is birth balance scale using the medical and then in the field of medicines, and the time of importance, and this is like the main data. These are like actually locked because they are transformed, because when the data is not normally distributed, then we can use this method to lock to transfer the data. We will cover this in the coming slides of the presentation. So now in this part we will cover whether we want to check whether this data is sit for the parametric or sit for non-parametric statistics. So as we talked in the previous presentations, previous slides, that we have to check in the three ways. We have to check first whether the data is the scale, like which type of data is this, whether it is the ordinal or it is the like ratio scale. Okay, the second one is we have to check for the normality, and the third one is for statistical test. Sorry, the second one is for the graphical representation of the data. From the graphically we will decide whether the data is normally distributed or not normally distributed, and the third one is to check for the statistical tests. So now let's check about the data. So when we see the ID number, so it is the scale. So it means it is the ratio scale. Okay. Then we come toward the age. Age is also the ratio scale. Then the like age is gender. So gender is categorical data. Gender is either male or female. So for the gender, we should not like do the test. Okay, because gender is the ordinal scale. So it is like the categorical. So it does not apply for the gender. And for the BMI, it is also the ratio scale, and work balance scale, time of importance. So all of these are actually the ratio scale, so we can apply. So we pass the first hypothesis or the first assumption that the data should be ratio scale or continuous data. So all of these except the gender, these are the ratio scale. So we pass the first assumption. Now let's come to the second assumption, which is the data should be normally distributed. So to check about the whether this data is normally distributed or not normally distributed, we have to come to here, the analyze, then come to the descriptive. Okay, after descriptive we select the explore option. So in the explore option, for example, if we check the age, for example, whether the data of the age is like normally distributed or it is not normally distributed. So for the age we have to shift to the dependent list. In the dependent list, let's come to statistics. And the statistic we have to check the descriptive. Okay, the descriptive, and then if sometimes it is selected by default, so no need to select again. So it is in this case it's also selected by default. Now continues. Now come to the plots, and the plots we need stem and leaf and histogram. And the second one you have to select the normalities plots with tests. Okay, and this you give the Shapiro Wilk test and the Kolmogorov test. Okay, so when you take this one, okay, continue. Then come to the options. In the options extreme case, it's not important, just leave it as it is, and then press OK. So when you press OK, so the SPSS will automatically analyze your data and give you all the detail about your data. Okay, this is like the property of the continuous data or ratio scale. Like they give us the mean, 5% trim mean, medians, and variance, and everything. Okay, kurtosis, skewness. So from here you can do the second, like in the normality. As we talk in the normality, we can check the normality by three methods: by the descriptive, by the graphical, and by statistical tests. Okay, so now come toward the graphical. This is first is the graphical representation. So in this way, the according to statistician, we have to compare the value of mean and 5% and the 5% trim mean. So you see it is 59.52 and the 5% trim mean it is also 59.50. So it is nearly same. So it's mean the value is the data of the age is normally distributed and this by this assumption by this values. Now we compare the mean and median. So come to the mean, the median is 59.52 and the median is 58.50. So it is also nearly similar. Okay, just only few digits on difference, so it's also considered as a normally distributed. Now come toward the skewness and kurtosis. So basically what is skewness and what is kurtosis? Skewness is actually like it's equal to the symmetry of the curve, whether your curve is like the bell shape, like this is a proper symmetry, or the curve is like deviated, like the tail is shifted either to the right or either to the left. So if the skewness, if the data is positive, so it means the curve, the tail is shifted toward the right. But if the skewness is negative, so it means the tail is shifted toward the left. So in both cases, if it is positive or negative, so it means the data is not normally distributed. So there is some skewness in the data, some outlier in the data. But there is one other assumption that if there is a positive or negative value, if the value is zero, so it means the way in the ideal case, if the value is zero, so we assume the data is normally distributed. But according to statistician, if the value is less than one, so we can also assume that data is normally distributed. Okay, so in this case, it is also past this assumption. And in the kurtosis actually gives us the idea about the peakness or the flatness of the curve, like how peak is the curve or how flat is the curve. Okay, so if it is negative, so it's mean like it is shifted toward the toward the left side, or if it is like positive, so it means it's shifted toward the toward sorry, if it is like if it is positive, so it means it is a high peak. But if it is negative, so it means it is low peak. It is like I will show you in the coming slide, like what I mean by the high peak and by the low peak. Okay, in the histogram, when we're talking about histogram. So here you just have to keep in mind, like if the value is very high, greater than one, for example, so we assume the data is not normally distributed. But in this case, it is 0.9, so it is not too much high value, but it is negative, so it means the peak is very low. So it means the data is normally distributed because the value is very low. So we pass from this area from skewness and kurtosis. We pass from the mean and median comparison and mean and 5% trim mean. Okay, so according to the descriptive, the data is normally distributed. Now come toward the second part, which is actually the statistical tests. And the statistical test part, here I have to mention one other point. If our data is like less than 50, so we can apply the Kolmogorov or Shapiro-Wilk test. Both are good, but statistician mostly prefer Shapiro-Wilk test. Okay. Okay, but if the data is greater than 50 or it's 100 or more than 100, so we apply Kolmogorov goodness of fit test. I will give you the idea about how to apply this in the coming slide, in the coming part of the presentation. Okay, so here the statistician assumption is that like if the data will be normally distributed, we look the significance value. Here, if the significance value, the p value is greater than 0.05. Okay, if the p-value is greater than 0.05, so we assume the data is normally distributed. The same for Shapiro-Wilk test. If the data is greater than the significance, the p-value is greater than 0.05, so we assume the data is normally distributed. So in this both cases, it is greater than 0.20 is greater than 0.05. Here 0.20 is also greater than 0.05. Here you don't confuse the real significance value when we analyze between the group, the normal significance, the t value and the t test or the ANOVA test or any other test. In that case, we say that the result is significant if the p value is less than 0.05. But for in the case of normality, the data will be normally distributed if the p value is greater than 0.05. So here you have to just a little bit controversy. You have to keep this in mind. Don't confuse this with the significance of result. Okay. Now we also, so this data also clear the age also pass the second assumption about the tests, okay, or the normality. Now come to the third assumption, which was actually the graphical representation of the data. So the graphical representation is actually first thing is look for the histogram. From this image, we don't actually conclude whether this data is normally distributed or not. So that's why we need a bell-shaped graph, a bell diagram for this graph. Okay, so we select it, double click. When you double click, you get this window, and this window you have to select this, the bell-shaped graph. When you select, then SPSS will automatically, by default, they will draw a graph for you. So now close from here and also from here, so you see the graph here. So when you see here, it's completely like it is the bell shape. So when the data is like the bell shape, so it means like the same distance of the tail from the left and the same to the right side. So it means it is anatomically bell shaped. There is no left and right. Okay. And now let's talk about the skewness and kurtosis. The skewness is that you will see the peak is toward either toward the right or toward the left, or either you will see the tail will be shifted like more toward the right or either toward the left, depend on the positive or negative value. If the data is positive, then it will be shifted toward the right, and the peak will shift it toward the left. Okay, but if it is negative, then the tail will shift it toward the left, and the peak will shift it toward the right. Okay, so you have to keep this. But and about kurtosis is the flatness of the curve. Like if the data have like for example have the positive kurtosis, if the kurtosis value is positive, so the peak will be like this. It will be very high peak. Okay, but if the kurtosis is very like the value is low, so the peak, the data will be like this. It will be spread, but the peak will be small. This is actually the peak of the data. So if the positive, so the peak will be somewhere here. Here the peak will be here. But if it is negative or low value, so the peak will be here. Okay, so you have to keep this in mind. But if this is like in atomic, it's complete symmetrical bell shape, so it means the data is normally distributed. Now coming toward the stem and leaf plot. In the stem and leaf plot, actually you also draw the bell shape. I don't have a marker here, but just you have to draw the curve like this. Okay, start from this end and come toward this end toward the 9, and then come back again toward this 5. So it is also like the bell shape. If it is also like the bell shape, so it means the data is normally distributed. Okay, and now coming toward the QQ plot. In the QQ plot, you can analyze like this. There is a diagonal line. So all the data that are aligned alongside of this diagonal line, so it means the data is normally distributed. But if these data, actually these dots represent the data. If these dots somewhere here, here, or here, or here, so it means the data will be not normally distributed. So the QQ plot also shows the data is normally distributed. Now come to the distended normal QQ plot. Okay, for the age. So here, this midline represents the mean of the data. Okay, so there will be equal number of the data spreading above and below of this line. So you see the same, approximately the same number of data is here and the same number of data is here. Or some statisticians say that you have to draw the S letter. So it's nearly the S. Okay, so mostly the data will be spread like S. Okay, the alphabet S. So if it is like S, it is more like S. So it means the data is more ideally like normally distributed. Now coming toward the box plot, this is the final plots that we can assume whether the data is normally distributed or not normally distributed. Here is the like the this is the box plot. Okay, the lower end of this plot represent the 25% of the data, and the upper end represent the 75% of the data. Okay, and the middle, actually this data, this is your mean. So the mean represents the 50%. This represents the 50 of your percent of your data. So in the ideal case, if the data is ideally normally, so this line should be in the middle of this box. Okay, but you can consider the data normally distributed if there is no outlier, no data here or no data here, no upper end and no lower end. But if this is like this data was not normally distributed, so you will see some data here or some data here. Okay, some dots here and some or some dot here if they have positive extreme or negative extreme values. So then you can assume the data is not normally distributed. So here, like it is not in the mid case, but there is no outlier in this data. So we also assume the data is normally distributed. Uh, as we talk about in the previous parts, that if the data set is greater than greater than 50 or it's 100 or above 100, so for the checking the normality, so most statisticians prefer that we should use Kolmogorov syndrome codes of fit tests. Okay, so for this, like I open the another SPSS file, so you see here that the data set. So you see the sample size is here 100. Okay, so we have 100 sets. So in this case, we don't use the previous method like descriptive and explore part. But in this case, if our data set is greater than 50 or 100 or above 100, so in this case, we have to apply another test, which is called I Comograph small bodies of fit test. So we come to non-parametric test, and here we select the legacy dialog. And the legacy dialogs, we come to the one sample KS test. Okay, one sample KS test, come to here. For example, in this case, I want to check, for example, again, we select the age, for example, okay, age. Or I will select here something different, okay? For example, here I select the quality of life, okay? Quality of life I select and will transfer it to the test variable list. Okay, then we have to select okay, no, select something here, and then we have to select descriptive here in the option. We have to select descriptive, okay, and then continue. Then we have to select the normal. Okay, just this is sometimes select by default. If it's not selected, then you have to select normal. Okay, then press OK. So when you press OK, because it is non-parametric part, so it's non-parametric KS test for quality of life. Okay, so you hit, this is the normal description. Just you have to check the sample size is 100 and mean, median, and standard deviation, and minimum and maximum value. Okay, now the main thing is here. The main part is here. Okay, so in this case, we have to analyze, or you have to look for to tell like significance value. It is 0.020. Okay, so here again we apply the same rule, that if the p-value, the level of significance, like the p-value is greater than 0.05. Okay, I repeat, if it is greater than 0.05, so it means the data is normally distributed. Okay, so in this case, you see it is greater than 0.05. It is 0.20, which is greater than 0.05. So it means our data is normally distributed for the sample size greater than 50. Okay, so this was about the everything about the checking the normality of the data. So to confirm whether our data is eligible for parametric test or not, or not. Okay, so now that's it. Let's come to the presentation again. So as we assume that from descriptive, from graphical inspection and statistical analysis, now coming toward the next slide, like this is the main slide. For if we assume, if all the assumptions are assumed that in our data is normally distributed, then if these are the conditions compared to independent sample, then we use independent t-test. If the two related sample, then we use pair t-test. If different several independent sample, then we use ANOVA. But if our data is not normally distributed, then these are the counter test for these type of if the condition is this, then we use chi-square test. If the condition is this, then we use this type of test. This depends on your data. If it is normally distributed and you want to compare two related sample, then you use sign test. Okay. This is the main graph that you have to keep in mind. Now, disadvantages of non-parametric testing, like why we want our data to be normally distributed. Okay, because there is several disadvantages attached to the non-parametric data. For example, the first thing is the normal, like non-parametric statistics. It actually give us the data, the analysis on basis of proportion, on the basis, or give us the analysis on the proportion of the percentage or the ranking. So it doesn't give us mean, median, mode, and like the more clear picture of the data. Okay, so that's why we prefer to use parametric statistics rather than non-parametric statistics. Okay, So like do not use all the information in the sample like throwaway information. Okay. It is less sensitive than parametric test. Like if we want to check the significance and we use the parametrics, so we get the more significant result if we use the parametric statistics. Okay, and do not accommodate it does not, yeah, do not accommodate the complex clinical design. Okay, and the third one is it is less powerful than parametric test with equal sample size. Okay, so it is doesn't give us more accurate information, more clinically relevant information. So that's why we prefer parametric statistics. So then come to the data transformation. Okay, if our data is skewed and but still we want to use the parametric statistics, then how can we transform the data so that it passes the assumption of normality? Okay, like for example, if the your first data is skewed, but you want to make them into the normal, transfer it to the normal distribution, then how can we transform it? So these are the methods. For example, if it is moderately positive skewed, so we use square root methods. This one, ADL. This is ADL, and we have to select here all, and here in all we come to the log. This is all written in alphabetic order, so we come to the L section, so log 10, and then transfer it there. Sorry, I just wanted one thing. We don't need to select first. We have to select first log, and then in the question mark, we have to transfer this to here. So then when you do this, you have to yes, okay, okay. So when you do this with SPSS system, it has automatically transformed your data into the log. Like compute your data. This is like sorry, this one is not. This one is our data set. So this is ADL and this is log ADL. Like it is transformed now to the normal distributed data. So if you check the analysis, you check the the normality of this data and compare it with this data. If this is not non-distributed, then this will be completely normally distributed. So it will clear pass all the assumption of like the descriptive analysis and the particle analysis and the statistical test. So if you check this one, so this was all about today presentations. We covered the main three things like when to use parametric and when to use non-parametric and how can we define what data is non-distributed or not non-distributed and how can if the data is not non-distributed then how can we transform it.